Hello and welcome to our video for lesson 3.4 over perpendicular lines. Today's objective is to prove and apply theorems about perpendicular lines, and we will begin with a warm-up. Once again, before we do the warm-up, before we do any of the rest of the video, please make sure that you have used your textbook to go ahead and fill in any vocabulary in this lesson before we begin. That's going to make the video that much easier to understand. So, pause the video for a few moments and do these following 5 problems in the warm-up. It might take you a little bit more time than normal, but go ahead and apply what we've been talking about in algebra for solving these equations. Alright, hopefully you've had enough time to complete the warm-up, and these are the answers we should have gotten. These are the answers we should get. In this one, you add 5 to both sides, so x is less than 13. But in number 2, you have to be careful. If you choose to subtract 3x from both sides, then 1 is greater than negative 3x. We could flip that around and say negative 3x is less than 1, so that x is on the left-hand side. But when you divide both sides by negative 3, you have to change that to a greater than symbol. You have to flip the symbol when dividing by a negative. So we would say x is greater than negative 1/3. For number 3, dividing both sides by 5 tells you that y is 18. And number 4, when you solve this equation, x is 15. Number 5, the system of equations. The best way to do this is actually just to divide both sides of this equation by 6, so that y is 15. This is actually a method called the substitution method. Because we only have one variable in this first equation, we just divide both sides by 6 to get y is 15, and then we can plug that into the other equation to find x. Doing so, x is 10. So your answers are y equals 15 and x equals 10. We will use some of this algebra throughout today's lessons. So let's go ahead and get started. Today's vocabulary will cover perpendicular bisectors and the distance from a point to a line, as well as some theorems that we look at. These are the definitions that you should have for perpendicular bisector and distance from a point to a line. Perpendicular bisector is a segment, or of a segment is a line perpendicular to a segment at the segment's midpoint. And the distance from a point to a line is the length of the perpendicular segment from that point to the line. So let's take a look at example 1. Here's what we need to do in example 1a. Name the shortest segment from point A to line BC. Well, that's the perpendicular segment from that point, and so the shortest distance from a point to a line is the length of the perpendicular segment, so AP is the shortest segment from A to line BC. Now, if it's the shortest segment, you know that the longest segment of a triangle, longest side of a triangle, is always the hypotenuse. So in our triangles here, this bigger triangle is split up into 2 smaller triangles by AP. In this triangle on the right, we know that AP has to be less than AB because AB is the hypotenuse, it's the longest. But in this triangle, we know AC is longer than AP, so we can write an inequality. We know that x minus 8 must be greater than 12. Since AP is the shortest segment, AC has to be greater than AP. So if we substitute in those values, x minus 8 is greater than 12. If we solve this for x, we're going to add 8 to both sides and get that x is greater than 20. So let's try another example on your own. In a very similar fashion, we have this set up here. I want you to name the shortest segment from A to BC and write and solve an inequality for x. Go ahead and take a few moments. When you are ready to begin, we'll check our answers. Alright, hopefully you had a chance to pause the video and work these out. Let's see what you got. On part A of this second part of example 1, you should have gotten that the shortest distance from point A to line BC is segment AB, right here. Segment AB. And then to write and solve an inequality, we remember that AB is the shortest segment, so it has to be less than 12. We know AC has to be greater than AB here. So we can substitute in these values. Here, 12 is greater than x minus 5. If you add 5 to both sides, you get that, sorry, that should not be 20. We'll make a quick correction here. Let me make that correction. Hold on just a moment. Alright, there, that looks better. We should get 17 is greater than x, so x is less than 17 is what our answer should be. Sorry about that. Anyways, we'll keep moving right along. We have these theorems that we've talked about, and they deal with perpendicular lines. First, if we have two intersecting lines that form a linear pair of congruent angles, the lines have to be perpendicular. The only way that two angles can form a linear pair and be congruent, meaning they're supplementary and congruent, is if they're both 90-degree angles. If these are both right angles, these have to be perpendicular. You'll notice this does not have a proper name highlighted in blue for 3, 4, 1. So if we're going to use this in a proof, we're going to use this form of writing it. Two intersecting lines form a linear pair of congruent angles, then the lines are perpendicular. This is what you would use in a proof, this phrase in parentheses, as a reason instead of writing it out all in words. We don't have a proper name. You can't just write 3, 4, 1, so you'd have to write that. But if you look at 3, 4, 2, that does have a proper name, the perpendicular transversal theorem. It states if a transversal is perpendicular to one of two parallel lines, it's actually perpendicular to the other line as well. 3, 4, 3, if two coplanar lines are perpendicular to the same line, then two lines are parallel to each other. So if T is parallel to both R and S have to be parallel. And once again, there's no proper name, so we would use this notation in a proof. Two lines perpendicular to the same line means that the two lines are parallel. Let's keep going right ahead with the rest of our lesson. So, in example 2, we've got a proof that we need to work on. Here's what we're given. We have R and S and T. R and S are two lines cut by a transversal T, but you're told that the given information, R is parallel to S, and angle 1 is congruent to angle 2. So to prove that R is perpendicular to T, we're going to take the following steps. First, we're going to state our given information. R is parallel to S, angle 1 is congruent to angle 2. That's given. Because R is parallel to S and 1 and 2 are congruent, we can say the rest. Looking at the first statement, R is parallel to S tells me that 2 and 3 are corresponding angles, so they have to be congruent by the corresponding angles postulate. But we know 1 is congruent to 2. Now we know 3 is congruent to 2. We can state 1 and 3 are congruent by the transitive property of congruence. And if 1 and 3 are congruent, we have a linear pair of congruent angles, so these lines must be perpendicular by that theorem we just looked at. If two intersecting lines form a linear pair of congruent angles, then the lines are perpendicular. Let's go ahead and take a look at example 2b. Here's what we're given. In this diagram, EHF is congruent to HFG. Well, these two lines cut by this transversal HF form alternate interior angles that are congruent. You need to recognize that, and we'll use that in our proof. But we're also told that FG is perpendicular to GH. That will come into play in just a moment. So we're going to start off by stating just the first given so that we can make that connection to the alternate interior angles that we just talked about. If these two angles are congruent, that tells us EH and FG are parallel by the alternate interior angles converse. If those are parallel, and we also have this other given information that we need to state, we have these lines are parallel. Sorry, that should be the perpendicular symbol. That's what was given to you. Then we can say that EH is perpendicular to GH by the perpendicular transversal theorem. We have HG that is perpendicular to one of these two parallel lines, so it's perpendicular to the other line as well. All right, one last thing to take a look at here, and that is if we are given this diagram and the measure of angle 1 equals the measure of angle 2, we can conclude, if we know these are equal measures, we know they're congruent. One of our theorems today tells us that P and M must be perpendicular. If we are given that the measure of angle 2 is 90 degrees and the measure of angle 3 is 90 degrees, then we know P is perpendicular to both M and N. So we could say that M is parallel to N by the perpendicular transversal theorem. And lastly, if we are given that the measure of angle 2 is 90 and we know M and N are parallel already, we know that the measure of angle 3 must also be 90. If one line is perpendicular to two parallel lines, or one of two parallel lines, then it is perpendicular to the other. Alright, that concludes the video notes for lesson 3-4. Please feel free to ask any questions that you have during class.